So today I will be presenting about classifying chest X-ray COVID-19 images via transfer learning. So I'm Jimut from Department of Computer Science, Ramakrishna Mission Vivekananda Education and Research Institute. And this is my collaborator Nilan Pal, who is from Department of Physics, University of Calcutta. So let's dive into the introduction first. So COVID-19 has changed the way humans interact with the world. It is one of the events in history where humans has thrown almost everything to fight the pandemic with science and technology. So for this study, we deal with the application of transfer learning in classifying chest X-ray COVID-19 images with high accuracy, sensitivity, and specificity. So medical sectors have a tremendous opportunity in applying artificial intelligence and deep learning for leveraging the diagnostic process via automation. So for this study, standard deep learning architectures were used as backbone to classify the given dataset, which was retrieved from this challenge website. So the models used here were previously trained on ImageNet dataset and were fine-tuned to get desired results. So let's talk about the dataset first. So there are three classes present in this dataset, as shown in the right. So there are 5273 pneumonia images, 7966 COVID-19 images, and 8151 normal images of different shapes and size, like 512 cross 512 and 1024 cross 1024, both 3-channel and grayscale. So there was a mix of data. So from the data distribution, we can see that there is a minor class imbalance. And the distribution of training and validation is shown here in this slide. So before passing it to the model, we had resized the images in 360 cross 360 size with 3 channels. And we have also normalized the intensity between 0 and 1 before passing to the model, since that is a standard way of training large data sets. So let's talk about model structure. So the architecture of the model, which was used to check the performance of validation dataset, is shown in this figure. So this is the general architecture of the model. So we have used a backbone model as convolution part of the standard architectures that were taken into consideration for the study. So this is the backbone model. So after applying the backbone model, that is stripping off the fully connected layer from the standard architectures, just the convolutional part. So after applying the backbone model, we used a global average pooling, and then we have used 3 layers of neurons, that is a fully connected dense layer of 128 cross 32 cross 3 neurons. So the output layer have 3 neurons corresponding to the 3 classes with softmax as activation function. So now let's move on to the metrics and results on the validation dataset. So for training the models, we have used a standard loss function, that is categorical cross entropy, which can be written as this equation. Here Ti is the actual class and Si is the predicted class. So this is the loss function when we have 3 classes. So for comparing the differences in metrics, we have used accuracy, sensitivity, and specificity, which can be written as these equations, where TP is the true positive, TN is the true negative, FP is the false positive, and F is the false negative. And for the optimization part, we have used Adam optimizer with a learning rate of 1 e to the power -4. And all the models were made using TensorFlow and Keras framework in Python 3 language. And this code will be available shortly in the website in GitHub. So we will be sharing that in the paper, the link. So now let's talk about the results on the validation dataset. So standard architectures have been used and were tested on the validation dataset by using the same model as shown before that we have shown. And the result obtained from the training is shown here. And due to the limitations of memory, different batch sizes were selected, and the details of each of them are shown here. Okay. So it is worth noting that Inception V3 backbone performs better than all the other models in the validation dataset by training on the training dataset. So we can see that Inception V3 gives an accuracy of 97.57%, sensitivity of 95.98%, and specificity of 98.27%. So we have also plotted the graph across 50 epochs, which is shown in the next slide. So we have plotted the graph for accuracy, loss, sensitivity, and specificity for all the 8 models that were taken into consideration. Now let's talk about confidence of the deep learning models. Now what it sees when we are testing it on the validation dataset. So Since the VGG16 model has a relatively good result, it has been selected to check the confidence by providing different images. So each of the samples shows whether a class is classified correctly or is misclassified when provided to the VGG16 model. So whenever a model is making any wrong prediction, its confidence lies in the wrong class. So for example, here a COVID-19 image has been predicted as pneumonia with high confidence, but it is actually COVID-19. So it is also showing with some confidence that it is COVID-19. Similarly, a COVID-19 image is predicted as normal image with high confidence, while it is COVID-19. And here a COVID-19 image is predicted as COVID-19 accurately. Okay. So this makes it really challenging to see what actually the neural network models learns and what exactly motivates the model to make a particular decision. So this might help medical practitioners to check the authenticity of predictions of deep learning architectures. So now let's look at the visualization of the filters learned. So we have made some effort in visualizing the filters that the neural network architectures have learned. So we have selected the VGG16 model before transfer learning. These were the textures in the initial layers, and these are the patterns that were learned in the final layers. So similarly, when this is for the model before transfer learning for the convolutional backbone. So after the training, we can see that the filters change from recognized textures and pattern of natural imagery to chest X-ray image features. So even the color changes from natural imagery to grayscale. So this natural imagery, these textures was got from the ImageNet dataset, which was it was pre-trained on. So we can see that the model learns to recognize problem-specific features, problem-specific patterns. So now let me hand over this slide, the presentation to my collaborator Nilayan. So he will be presenting. So is Nilayan here?
Yeah, I'm here. Thank you, Jimut. Now I'll be taking over. So as you could see in the previous slides, the predictions of the deep learning models were quite confusing, and we did not know why it selected a particular class for a particular image. So we have dedicated the next few slides to actually justifying this confidence of the neural networks through a method called GradCam. One of those sets is actually shown here in this picture. So this shows actually a COVID image properly detected is a COVID class. When we initially supply the image to the model, the initial layers actually learn the overall structure of the lungs, which is shown in the second image. But as you move on to the deeper layers, you can see that it actually pinpoints some specific areas within the pictures, which it thinks is actually providing it the confidence to make that prediction. So as you can see, again, when the COVID image is detected as normal image, the same things happen. But here, as you from the difference is actually in the final layers. As you can see here also, specific points are highlighted, which are for different predictions. So the model is actually taking into account confidence from the initial layers to the final layers altogether. We have also shown the same for when a normal image is actually detected as COVID or a COVID image is detected as pneumonia. Here the same thing happens. Could you go back? Yeah. So you can see that initially it learns actually how the shape of the lungs and overall structures are. But as we move on into deeper layers, it starts to highlight specific areas within the image. Sometimes this is incorrect because as you can see, when the normal image is detected as COVID, in the fourth image, it also highlights areas within the bone, which is in the image, but that is not relevant really. Okay, now we'll talk about the ablation study. For ablation study, we took an input image size of 500 cross 500 pixels, fully connected layers of 1024, 3 neurons, dropouts, other combinations. We also use the models VGG16 and Inception V3. For those features, when those features were not used, we use the standard input image size of 360 cross 360 pixels or fully connected layers of 128, 3 neurons. Then we noted the performance of the two models for the different input features. Could you go to the next slide? Yeah, so in this table, as you can see, we have noted down the performances, the metrics. So for VGG16 model, you can see that when we combine all the three features, it actually gives an accuracy of 96.96% and a specificity of 97.82%. But when we look at sensitivity, it's 94.91%. However, when we remove two features, namely the image size and the dropouts, and only concentrate on the dense layer size, then we see actually the sensitivity going up to 94.99%. Again, but when we move on to Inception V3, then also see that when we combine the three features, the metrics actually take a nosedive. But when we remove one of the features, the dropouts, then actually the metrics were the best among all the ones that we obtained. So what we can conclude from here is that the results of a particular substructure might not give better result when the backbone model is changed. As you can see, when we change from G16 to Inception V3, but we considered the same feature sizes, the metrics were actually different. Also, it is not necessarily true that the overall performance of the deep learning architecture will increase if we combine individually well-performing substructures. This is also evident when you saw that when three features were combined, it did not always give the best results, which is clearly visible for Inception V3. Okay, and then we'll talk about the results on the test set. So when we evaluated this model on the test set, which was actually unseen, so the metrics were a little bit lower compared to the validation data set, as you can see in the table. So this could be due to the fact that the distribution of the test data set might be different from the distribution of data of the training data set. Also, you can see in the table that when we combine the training validation data set and then train the model and this combined data set, then also the metrics were a little bit lower. So this is also might be attributed to the difference in the distribution of the combined train and validation data set from the individual train and test data sets. A final model was trained on just the train data set and then tested on the unseen test data set. On the right hand side, you can also see a confusion matrix for Inception V3. This was actually obtained when we tested it on the validation data set only. So the diagonals in this matrix show the true positives where normal image is identified correctly, a COVID-19 is also predicted correctly, and same goes for pneumonia. But one thing which is very special to note here is that a normal or a pneumonia image is actually never identified as COVID-19 image.
Let's slowly start finishing up.
So finally, we move on to the conclusions and limitations. Firstly, we would like to point out that this transfer learning shows that the performance of the deep learning architecture can be improved significantly without the use of data augmentation. This is a serious issue because for medical data, where we are not medical experts, we could not just use data augmentation without referring to proper methods. Also, through ablation studies, we showed that the combination of different substructures, which performs individually but good, might not result in a better overall performance. And finally, the model actually performs best on the distribution of data set on which it is trained. So actually bringing data from slightly different domain might result in degradation of performance. So this is why we should not use this as a diagnostic tool. And then finally, some future works which might be possible. First of all is about the domain adaptation thing. So if we actually combine data from different domains, so that might help the model learn domain invariant features. So this is called domain adaptation, and this might be used to increase the performance of the existing model. Also, we can employ neural architecture search to find the best model for a given data set, but that proved to be a computationally expensive task. Otherwise, using attention model and building different substructures might increase the overall performance of the models. And finally, we'd like to thank the organizers of CXR COVID-19 challenge for their efforts in sharing the data set. And also, we are grateful to one of Jimut's instructors from his Institute for Engineers of Machine for this study. And finally, some references.
All right.
Thank you.
Thank you guys very much.